Welcome to our NPTEL courses, that is power quality improvement technique. This is we are going to discuss about the hybrid active power filter. Already this will be our third lecture on the hybrid active power filter. Now this hybrid, we have seen many combinations of the hybrid active combination. This is one practical circuit. This has been reported by Akagi in 2005, and it is a low cost transformer less hybrid active power filter, and you can see that it is a 480 volt 60 hertz supply, and and receiver's voltage is maintained to the 105 volt, and you this is a filter, and this has been tuned to the some desired frequency, fifth or 7, it has been tuned to the 7, and the passive filter power rating is 5 kVA, and the diode rectifier power rating is 20 kVA, and and with these combinations, the only you require the active power rating of the active power filter reduced to be 1.6 kVA, and we assume that source inductance will have around 0.15 millihenry, that is 0.5 or the base value. We take this as a base value, 480 volt 60 hertz, and only disadvantage is the topology, that you require to put one extra inductance, that is the inductance to smooth out the ripple. Essentially, when you have a load change, then what happen, this part will smooth out the rate of change of the load, and thus capacitor gets little more time to settle down. So, thus this extra entity we require for this configuration, and it is essential. And thereafter you have a CF, that value has been depending on the 60 hertz supply, and it has been tuned to maybe the 7th harmonic, and LF value is 2.5. These combinations will be essentially removing some amount of the 5th or 7th harmonic, and you cannot have very sharp Q factor here. Here Q factor of this filter required is maintained at 22. So, that some portion of the 5th harmonic also get eliminated. Also there is a required to have a real power exchange, that also, and you should not offer very high impedance for it. And considering that, the Q factor have to be optimally designed. So, whatever I discussed, let us put into the small structure form. This hybrid configuration results in a DC voltage as low as 105 volt across the DC bus of this active filter. Since it is, the rating comes down as low as 1.5 kilowatt, even you can use MOSFETs, and thus you can have a very high switching frequency, and also the cost of the component is quite lower. Moreover, no switching ripple filter is required for the hybrid filter, since you can use MOSFET or high frequency IGBT of lower rating, lower power rating. The hybrid filter, because of the passive filter presence, offers high impedance at 10 kilohertz. So, you need not have to have a extra filters to suppress the switching harmonics. Only demerits is that you require an extra components, that is, a diode rectifier has an inductance value of this, that is 5% at its AC site. This AC inductor is indispensable. So, you require to put it, this is not that, then you cannot have the desired power quality of IEEE 519 standard, IEEE 1151 or IEEE 514, whatever the standard you are trying to achieve, you will find without this inductor you will not be able to achieve that, and also you will have a sustained oscillations into the DC bus, because if it is the rate of change of the load current is very high, then and the value of IC cannot change very fast because of the high impedance, and thus what happen, it may collapse the DC bus voltage, and for this reason it is advisable to put the AC inductor here. And this has been implemented by Akagi by all the three controller, whether it is optimal control or whether all are required to be placed or not, that is a matter of research, but considering that paper we are going to discuss all this feedback. The control system of the hybrid filter can be feedback control, and I will show that ultimately, as you have seen throughout our discussions, you have IF or IC star, and from there you will have a, this will be actually you have a summer, and you will subtract the IF, and thus you will put to the PI or the hysteresis band. This part essentially your feedback controller. Similarly, you may have something feed forward controller, they will see that you have the ID of the some ID, that is the D axis current of this, and you can add maybe with a block of the fifth, and thus you add up. So, this will be a addition and this will be a feed forward control. Op amp in a hysteresis loop essentially a feed forward control. And thereafter you have a DC bus voltage control, because you again it is nothing but a feedback control. Here you will have a VDC star, and here you will have a VDC, from there you will have a PI, and you will add up with the ID component of this shunt active power filter. Thus, this is the overall control strategy reported by Akagi. So, you have the UPCC, that is nothing but a grid, that is the voltage, or let us tell VPCC basically. So, essentially the voltage at the point of common coupling. In some literatures, generally if you see the German notation, they write UVW instead of the ABC. So, these are two synonymous entities. So, voltage at PCC, so that will be fed to the PLL. PLL will generate the fundamental as well as the fifth harmonic component of it. So, 5 omega as well as the omega 1. Now, you have the source current of ABC or UVW, then it has been transformed to the ABC to DQ, first alpha beta, thereafter DQ frame of reference, and thus you get the fundamental of ID 1 and IQ 1. Then you have, then you pass this high pass filter, but realization is by subtracting with the low pass filter. Generally you have that low pass filter LPF, and from there you subtract. So, this block is essentially you can say that it is high pass filter, and thus you essentially got ID 1 delta and IQ 1 delta, and this part is essentially the DC voltage control. So, you have a VDC actual minus VDC star, you have a PI controller, and thus you have the small amount of ID, we generally say ISD. This will add up with the first fundamental component of the ID 1, and thus you can have this IDQ 1 and the it will be added to the ID delta, and this amount will be essentially your reverse is a quadrature axis, and then you will calculate your the current to be injected by the shunt active power filter, that is in a ABC or the UVW IF, and you will subtract it, then from there you will have a gain generally to this may be require some kind of scaling, and thus you get this VU, VV when VW, and this feed forward will be carried out like this. You will sense the load current, not the source current of the or any of the two phases, because you can of course generate the another phases by subtraction with the 0. Then this omega will be fit here, and you will have a dq transformation, but for the omega 5, and thus you get the fifth harmonic component of it, and this fifth harmonic component you can calculate. This will be d 5 and the q 5, and you feed this component and add up with here, because this is the component in the load current presence and this is the component in the source current presence, both required to mitigate, and you have decided that your passive filter will mitigate. For this reason there will be a difference, and you add up, and ultimately this will be the actual PWM signal for your hybrid shunt active power filter. Thus we can say that the feedback control forces all the harmonic current content in IL, that is load current, to flow through the hybrid filter, whereas it forces no harmonic current to flow from the power system into the hybrid filter. This improves the filtering performance of the passive filters and prevent the passive filter from being overloaded and ineffective. So, this is the way you have to taken into the consideration of all those aspects of the passive filters, and thus we require the three kind of control. First, let us talk about the feedback control. The feedback control makes the active power filter acts as a damping resistor for the lower order harmonics, so that no harmonic resonance occurs between the passive filter and the power system inductance. So, this is that the active damping can be achieved by this feedback control. And this paper that Akagi has put defines the volt ampere rating required to be the filter to be the 480 volt, that is the standard in Japan hybrid power filter as follows. So, that is a PHF, that is a power, that is a root 3 VDC and IF max. From there, for the same compensation for the hybrid filter, if you can calculate, so this require only 1.6 kVA, and whereas if you do the compensation for the 700 volt, that 480 volt line required to be maintained, then the power rating required to be the 16.36 kV for the normal shunt active power filter. But what you require extra apart from this LC branches, you require just extra that AC inductor, and thus there is a 10 times reduction in the power rating. So, this is the great achievement and in the field of the shunt active power filter. And let us now talk about the design of this passive part of this hybrid filter. The hybrid filter consists of the passive filter tuned to the 7th harmonic. Look, I have shown in the block diagram, that is the 5th harmonic is been extracted and put it like that, and thus main chunk left out was the 7th harmonic. So, for this reason passive filter is been designed for the 7th harmonic, and this has been found to be optimal. Because of lack of time I cannot go to this study, and I personally done the study. Instead of the why not you do what here, you can go back to our this block diagram side. This has been designed for the 5th harmonic, and we can do the same thing for a 7th harmonic, and thus your filter required to design for the 5th harmonic. It has been found that 5th harmonic, if you design for the 5th harmonic, the system will be more bulky and costlier, and for this reason it has been found to be more optimal solutions. And so, the resonance frequency of the passive filter, as you know, that is 1 by under root of LF into CF. So, resonance for the selections of the 7th harmonic are as follows. So, these are the passive filter is tuned to the 7th harmonic frequency, that is what I was telling, is less bulky than that tuned to the 5th harmonic, as long as both filters have the same inductance LF. Because if you put the value of the LF constant and you change the value of CF, then of course, the capacitor will be more bulkier. The passive filter tuned to the 7th harmonic frequency offers less impedance to the 11 and the 13 harmonic component compared to the passive filter tuned to the 5th harmonic frequency. So, this is also one of the reasons, and we are going for the overall cost optimizations and the performance optimization, that this topology fits rightly into the system. The feed forward control combined with the feedback control makes a significant contribution in improving the filtering performance at most dominating 5th harmonic frequency. The characteristic impedance Z of the passive filter is given by Z equal to under root of LF by CF. So, and this is also called the surge impedance, and these we will see this impedance determines the filtering performance, because this will offer at the 50 hertz. This impedance determines the filtering performance at harmonic frequency except the resonating frequency. So, resonating frequency may be your 7th harmonic. So, what will be the impedance offers? That will be in this value. Generally, the characteristic impedance should be low as possible, and thus what happen, you want to have a very high value of the inductor, that is one of the requirement. But there is an advantage of having small value of the capacitor, because you are using CF, you can switch it on, CF and CDC come in series. Thus, you got a voltage divider. Here this voltage is 480 volt RMS. If you multiply by root 2, then it is around 620 volt peak value. So, accordingly this voltage will divide. Since you know that C1 V1 equal to C2 V2. So, higher the value of the capacitor, lower will be the voltage rating. So, smaller the value of the capacitor, higher will be the voltage rating, that it will take the more voltage across the CF. So, it is for this it is desirable to have the lower value of the CF. But what happen, you pay the penalty in the cost, because cost of the inductor is higher. So, we can talk about detail in that subject. So, that but time due to time constant, let us move forward. This implies that the capacitance value CF should be as large as possible and inductance value should be as small as possible, so that your search impedance become lower, and but it is a direct conflict of your rating of the device. Your rating of the device will be coming down if the value of the CDC is more and CF is less. A lower characteristics impedance reflects lower DC capacitor, that is what I am saying, capacitor voltage, as well as the lower EMI emissions by the hybrid filter. This allow the hybrid filter to use low voltage, because rating is only come down to be 1.6 kVA. Low voltage MOSFETs, that is less expensive and more efficient than the high voltage one, because its conduction losses are quite low compared to this IGBTs, and also turn on turn off losses are quite low, and for this reason overall efficiency also improves with the MOSFETs. Now, low characteristics impedance and has a following disadvantages. If you have a low value of the Z, then you will have the following disadvantage. Large capacitor CF, that is what I said, makes the system bulky and expensive, keeping the constant value of LF of course. Large amount of leading reactive power to be flown into the filter. So, you will have how much reactive power handling capability, that also will be governed by this CF value. Smaller inductance value LF will increase the switching ripples. So, you cannot do that. So, you have to choose some value, optimal value, so that switching ripple does not reflect it into the source current, because you have not put any extra high frequency filter. The ratio of the switching ripple voltage occurring at the point of common coupling, with respect to that the AC side of the filter can be calculated under assumption that this, for this reason it is essential, load AC, that is inductor AC, is much greater than the source inductance. So, this is something it has to be valid, and if you have a large transmission line, but generally it is not so, then you may have a high source inductance, and there you may not require this condition to put the extra inductance before the diode bridge rectifier. So, and now some recent modification that has been aspired from the topology has been described. So, that is a combination of the power quality and the facts. Essentially you have a sources, and thereafter you put the fax devices like TCR, and this is a thyristors control reactor. Ultimately value of the inductance will depend on the firing angle of this thyristors. Please refer to my fax courses, there has been detail has been covered, and thus capacitor, thus this inductor values can be modified by changing the value of the thyristor. Thus what happened? So, these combinations also offer you the reactive power compensation, that is a task of the fax devices, and apart from that these combinations gives you the shunt active power filter. And this combination, and also you can have a switch of this kind of a full control converter maybe. So, this combinations, this is a combination of shunt active power filter with the thyristor control reactor. This is a marriage of this power quality and the fax devices, and thus it gives you a better solution. Same thing is possible with the another fax devices, that is TCLC. This will take care of the reactive part, and ultimately the harmonic part will be fed to this L and C. This will be tuned to the particular dominating harmonic, and thus you can get rid of this. Essentially, if you see LC and CPF, this is nothing but the same topology. Within that you have a controlled inductor through the switching, and thus you essentially have a 3 phase 3 wire TCLC of high pass active power filter. Now, this is the one of the topology that it is reported by me. So, here it is a main intention was of course in Akagi's paper. So, there is a only I have used one leg more, but and that too because of the power rating has been drastically diminished, you can use the MOSFETs, and ultimately this has been tuned to the 5th and 7th harmonic with a Q factor in around 40. So, that you can have a quite sharp resonance, and this has been tuned to the 11 and 13 harmonic, and we do not leave anything for the passive, because there is an issue of the detuning in case of the passive filter, hybrid filter also, because hybrid filter the passive part what you were trusting gradually it will decay, and thus for this reason we leave everything with the combinations of this is the part it will compensate 5th and 7th, this is a part it will compensate 11, 13, and we have found that value of LC, LSC what it is required found to be less compared to this Akagi's work. And one leg we have reduced it since it is a 3 phase 3 wire system. One leg it is connect to the end point of the DC bus, that there is no fracturations of the DC bus. You can connect the midpoint of the DC bus this leg. Then what happen if there is unbalance, there will be a problem of the DC voltage fluctuation. Instead of that we connect it in the negative half of the DC bus, and thus the fluctuations gets eliminated. And if this topology works very fine, and we have shown some results in our shunt active power filter, there is a topological improvement and it has the reduced cost solution of this Akagi's version. Same thing, there is a reduced switch, and here you connect the almost same, there is nothing new here from this topology, just you take the 2 legs, there is a 4 legs, and thus you have truncated that portion and you lay with the 5th and 7th, and this is 5th harmonic low pass filter and this is 7th harmonic low pass filter, and ultimately once you are mitigating, since you know that 5th and 7th will be mitigated by the passive filter, automatically the 3 phase receiver system other phase get controlled, and thus overall rating will drastically come down. It has been found that this rating is little higher with the same rating 480 volt of 60 Hz system, this rating will be 2.2 kVA instead of the 1.6, and that is also acceptable, there is not a big deal on it. Same way we can combine the same thing in a UPQC. So, this is the 3 wire UPQC with the passive component connected in a series part of it, and this is a shunt part of it, and thus overall rating of the UPQC can be brought far below than it, generally it will be 5 to 10 times. Another combination can be combination of the switch, that is the some portion of this topology will be common to the series and parallel with the hybrid filtered topology, and thus you can see, because this topology just have this 8 switch, it is called 8 switch UPQC, this is with the hybrid combinations, but overall switch rating can be reduced, but stresses across the switch is generally bring down by with the help of this LC filter, and but some devices here are rated higher because of the conduction time of those switches required to be more, and thus there is a many topological variation of this hybrid filter topologies, and these are the few important example I have cited here. Thank you for attention of, and I thus conclude this course almost, and you are welcome to ask questions, and this is the many thus we started with the journey from the overview and with the modern development with the shunt active power filter UPQC and its marriage with the fax devices. Thank you.